Hi, in this video I'm going to give you the details of the physical layer in terms of the OSI model. So as you can see, we have these 7 layers and we are now at layer 1, which is the physical layer. This is the layer that is responsible for the encoding of binary digits, the binary digits which represent the data. Here humans or machines have made data. It goes down the OSI layers to the transport layer, network layer. I've already got videos on this, data link layer. And now we've got all this data, all these bits, which we now need to encode, send on the transmission channel. The channel might also be over the air, and then it will be received. So this is the layer that is to do with the signaling, the signals themselves. So you can see that in this picture, there are binary bits, binary data shown here. See, this is called bits, ones and zeros. Now, as I said, humans or machines create the data. Maybe you want to send someone an email. So there's your request for your email message, or maybe a request for a web page, or whatever it is. Then the application data is encapsulated with the data onto the data as a header. And that will tell the OSI model what application you're using and the services that need to be applied and so forth. Then this moves down the OSI model. Can you see this is a protocol data unit? There's the data. It becomes a segment at the transport layer. It becomes a packet at the network layer. It becomes a frame at the data link layer. Remember that each time the data moves down the OSI model, can you see that we keep adding headers? And then we get to the data link layer where it adds the header and the trailer. Now we need to get this information onto a network or onto a medium. And this is where we now need to deal with transmission and reception. So this is a physical layer. So if you want to know in a nutshell what the purpose of the physical layer is, it is to create the electrical, optical, or microwave signal that represent the bits in each frame. Now remember that networks do not only consist of hardwired media, meaning we don't only connect networks with copper, we also connect them with fiber optics, and that is why we say optical. Or we also connect networks using microwave signals, and that is why it says microwave here, because it is radio signals. Now I have some pictures here and I'd just like to show you them. There are many ways to get this bit stream onto a channel, onto a media. For example, we have to modulate it. Here are some modulation techniques. Here we've got AM. This is from the old days. It was called amplitude modulation. We've got FM. Now these are the analog modulation methods. FM, phase modulation, and pulse width modulation. In terms of digital modulation, we have a few as well. Phase shift keying, frequency shift keying, and so forth. We also have quadrature amplitude modulation. The point I'm trying to make is there are many methods to get the bit stream onto fiber optic or into the air or onto copper. Now here we have some binary digits, 0110. This is in a digital format. Now if we're going to transmit this over the air, we might want to modulate it onto a carrier wave. There's the carrier. The carrier represents a high frequency wave. And what happens is when we merge these two together using a certain technique, it could be amplitude shift keying, for example. Can you see how the amplitude is changing, which represents the binary digits? So as we see here, when this thing would be decoded, because this is encoding, can you see when I put the digital signal on the carrier wave? The carrier wave is a high frequency, a much higher frequency wave. The reason why it's much higher frequency is it's easier to send higher frequency waves through the air than lower frequency for various reasons. And that has to do with distortion, noise. Now, here we have the amplitude shift keying. There we go. Another option is frequency shift keying. Can you see how the frequency of the carrier is shifted based on the binary data here, the binary signal? So when it gets demodulated, remember this is modulation, going from this to that is called modulation. When we demodulate it, we remove the carrier signal and we hopefully will get the same digital signal. Can you see this is a whole transmission and reception process? And there's another option here called phase shift keying. By changing the phase of the waves, we can then encode intelligent information in this phase shift wave. Now, there are many methods of modulation, and this is just a list of a few. We've got different frequency modulation methods, continuous phase shift modulation methods, and then we also have the newer modulation methods which we are using, where I have this here. Yes, here are the LTE options, and this is where we're at now with the 4G and going into the 5G networks. And the LTE is the orthogonal frequency division multiplexing. Can you still see it is a modulation method? So even though it seems like a brand new approach, it still uses the principles of putting information onto a carrier wave and getting it out to the world. Right, so there we go. Here are some further pictures. I'm just showing you amplitude modulation. Can you see how the amplitude determines the intelligence? While here the amplitude stays the same in an FM wave, but the frequency represents the binary data. Can you see how the frequency increases here, maybe representing a 1, a binary 1, and when it goes back to the regular carrier frequency, it represents a 0. So we can encode binary information by representing it as frequencies. There we go. Higher frequency is a 1, lower frequency is a 0. And then we can also do that based on phase. Can you see there? Here we have a sine wave, for example, going up, down, but then it should have gone up again, but boom, 90-degree a phase shift there immediately means, okay, this is a change in the bit from, say, 1 to a 0, and then we had a phase shift again, so then that means it's going from a 0 to a 1. So we can put intelligence onto a carrier wave, and as long as the transmitter and the receiver both use the same modulation technique, then we will have a transmission and reception of intelligence information. All right, so we can also separate modulation from analog to digital, and I'm not going to go into that because that is out of the scope of this lecture. But what I want to show you is the process. We have an information source. Now recall that if we're looking at the OSI layer, let's just have a look here. Here is the information source. We as the users make communication. Maybe you want to get a web page. Maybe you want to send an email. There's your data. It goes down this OSI stack, and then it comes to the data link layer, which prepares it based on whatever protocol we're using for the physical layer. Now, the physical layer will then have its own additional rules, and these are mostly set by various standards organizations like ISO, IEEE, and so forth. These are mostly to do with engineering and radio communications. So the physical layer may even add some of its own headers, by the way, some additional signaling information, but this usually falls out of the scope of, say, the CCNA or the network engineers purview, because this is more the radio engineer. The radio engineer will know and understand the details of how to modulate, what the different amplification and antenna design and so forth, and all these additional things. So what's happening here is we've created communication. Now this communication has to leave our device. It needs to leave our device in order to get onto a network. So it has to be sent in a format that is relevant to the media we use. Are we using, for example, copper? Are we using glass, light pulses? Can you see this is what a fiber optic light pulse would look like, 1010. And we may even send it over the air, and that's what I was just showing you. A digital signal, there's the digital information that we are trying to send. Remember that computers speak binary, they don't speak analog. So there we go, AM. The digital signal has to be modulated, and there's the analog techniques, AM, FM, and phase modulation. The point is, when it gets to the other side, we can then convert, or let's not say convert, we can then demodulate and get this digital signal back. But while we have to go through a medium, maybe we are in one city and we need to get the information to another city, we might find that there are several different protocols used in the physical layer in terms of getting this information across. So if we look here, information source, that is usually us, it's our devices. Then that information is prepared by the data link layer, and the physical layer now literally has to transmit that information. When I say transmit, it has to get it onto a medium, whether it's glass, air, or copper, so wired. So there's the transmission, the transmitter. And what are we transmitting? The word is called a signal. We are transmitting the signal. Then there's a channel. Remember that we have to transmit the signal through something, where be it the air, be it copper, be it optical, glass, even a waveguide. A waveguide is another method of sending waves, but usually in a dedicated channel. Now, we also have the noise source. What is a noise source? Well, remember that once we try and send information across a channel, let's see here. Here we are with our cellular phone, and now we are trying to send information across a channel. This is over the air. Maybe you're sitting at college and now you want to send someone a WhatsApp message. Well, you'll be sending that over the air. And what do you know about the air? Well, there's dust particles, there's water vapor, there's trees that are blowing, there might be clouds, there might be some radiation in the air. So all of these things add noise. Even if it is a wired network, you might have dirty contacts. You might have cabling that has gotten like aged and maybe corroded, and the resistivity has changed. So all of these things add noise. And as you can see, here we have some cellular antennas. Remember, they're coming through the air. What happens if there's birds in the way? What happens if you are moving? Think about that. You are driving or running and you are trying to have a conversation. Well, that movement also interferes and adds noise. So all of these things interfere with the original signal. So all of that adds noise. That is why this diagram shows a noise source. It just means that the environment often adds some noise. Maybe you ran your cables next to some power lines or some high voltage or high current carrying cables, or there was industrial machines, or people were using drills or contactors. Well, that will also add switching noise, or even some spurious response, spurious spikes to your communication. And then we come to the receiver. That is the other person or the other node. Maybe it's a router, maybe it's an antenna, who is now trying to receive this signal and has to then forward it to the destination. So you can see this is the general layout of this process, and this is the physical layer. Now, just having a look at this, you can see how there are many different mechanisms for getting signals across networks. Here we have Ethernet or USB cable. Here we have Ethernet, and there's a spelling error there. Here is Wi-Fi. And you can see how we have different protocols. Here on the internet, we might have the WAN protocols, such as frame relay and so forth. And you can see here, there are many different protocols in GSM or radio networks. Now, in order for this information to be sent, we have to have frames which entail or have our data inside. Now, in order to do this, the physical layer needs to also know or have some idea about identifying frames. Now, the delivery of frames across local media requires the following elements. We need physical media and associated connectors. Think about it. We are trying to connect our nodes, so we need connectors. we need antennas, we need adapters, we need cabling. So this is the physical components. We also need a representation of bits on the media, and that's the signal. There's no point transmitting nothing. We are transmitting something, and that is bits which represent the user's data, most often in a modulated, encoded format. And then we also need encoding of the data and control information. Because if we just send the signals, when we receive those signals, they won't mean anything to us because we don't know who it's for, whether there were errors, when the frame started, when it ends. So do you understand that there's an encoding data and control information so that we may process this information? If I just walk into the shop and I say $10, what does that mean? Is that $10 for buying something? Is it $10 for paying wages? What does it mean? So information by itself is meaningless. We need to know who it's for, who sent it. We need to know the start point of the information and the end point. Because if I walk into a store and say dollars, it sounds like the sentence wasn't complete. So maybe I would say, I'm here with $10 to buy a packet of cigarettes. Now that makes more sense. So we need to know when the signal starts, when the signal ends, and when the next we need to know when the frame starts and when the frame ends, and when the next frame starts and when the next frame ends, and who it's going to, and so forth. All right, and the final thing, we need to have transmitter and receiver circuitry on the network devices. Remember, I showed you here in this diagram, we cannot just send information onto a channel. We can't just plug in an Ethernet cable and assume it's going to work. We need some sort of amplifier or transmitting circuit in order to prepare these bits for the media that is being used. If we're using optical, we'll need an optical coupler in order to get the bits converted to light and transmitted on the channel. So we need transmitting and receiving equipment or circuitry. So we're talking about the electronics here. Now, if you have a look, here I have a wireless card here. This is just a wireless, let me see, a wireless modem. I'm sure you've seen these before. These can be installed. Maybe you can use this for an alarm system. You might find on your motherboard you've got a wireless card, a Wi-Fi card, whatever. I'm sure you've seen these before, 3G dongles that you plug into in the old days, into your computer, and you would have access to the cellular network. Well, guess what? There has to be some sort of transmitter. And you'll see that here we have circuitry that allows us to transmit the information. So we can't just have the connector. We also need electronics that allow us to couple or get the bit stream, the signal, onto the medium. Right. Now, having a look at the standards, we can see that there are differentiations made here between what is done in software and what is done in hardware. Now, in my previous video, the data link lecture, I explained how the data link marries the software layer into the hardware layer. Now, we are busy with the physical layer, which is the layer of just the hardware. Now, you can see that for the most part, there are different standards organizations that deal with the different standards for each one of these layers. Now, what I'm trying to bring to your attention is that in terms of OSI and network engineering, everything we do is governed or set out by various standards organizations. And the reason for this is if we have a standard, then everybody does the same thing, then we don't have problems with compatibility. So if I take my laptop to a different country and I go to Tokyo in Japan, it will still work because they comply with these same standards. And then if I go to Perth in Australia, it will still work if I'm on a Ethernet network, for example. And this is why we can buy cellular phones in other countries, because for the most part, the technology works, although some network operators tend to try and lock phones. That has nothing to do with the cellular radio aspect in terms of how the technology works. That's just locking the IMI, the IMEI number, so that you can't have access to the network. But the inner workings of the phone will be adhered, will adhere to your network and to your network overseas because of these standards. So if you buy a brand new laptop, the laptop will work in any country, and it's because of these standards that we use. So it's very important to understand that standards govern what and how we do things in terms of the OSI model. Now, why they have this slide here is they're just showing you that there tends to be slightly different standard organizations to do with the physical layer, because it is this layer that we are dealing with physical components in terms of materials and specification in terms of how the materials are made and how long they may last, and in terms of their physical properties. And we also deal with encoding and how signals are encoded, and also the signals themselves. So this is why we have these groups here, as you can see, IEEE, which is a very popular one, and that is the Institute of Electronic Engineers. So you can see this is now we're getting more towards the engineer level. And I know that in networking people, in computers, people generally throw around the term engineer, but the engineer, in terms of a certified engineer, is mostly linked to hardware understanding, and in terms of how hardware operates, because that is what they spend a lot of their time studying in terms of mathematics and electrical components. All right, so we move on now, and we did have a look at the signals, and there we go. The signals is the information which we want to send across the network. There are the connectors, and there are many different types of connectors. As I've shown you here, we've got the Ethernet, and you can see the fiber. And then in earlier times, we used a lot of the serial connectors. And as I said, the point-to-point protocol, V35, frame relay, and so forth. So all of these were utilized at some point. And there are some cables. As you can see, we've got a RJ45 connected to some patch cable here, which will be plugged into this network interface card. Now, the process of encoding. Encoding is a method of converting a stream of data bits into a predefined code. Codes are groupings of bits used to provide a predictable pattern that can be recognized by both the sender and the receiver. It's very important that you understand that when we encode something, if the receiver does not know the decryption algorithm, how to decrypt it or use this signal, then there's no point. So this has to be shared between transmitter and receiver. In some communication methods, we send the decryption algorithm with the signal, but that is out of the scope of this course. Now, the signal is mostly, in terms of digital signals, a 1 or a 0. There we can see it is binary data. But keep in mind that when we're on the physical layer, the signal might be in various formats. It could be electromagnetic waves in the air. It could be light impulses. It could be voltages in a wire or traveling in a wire, the current in a wire. So the signal could be represented by different physical or physical properties, light signals, waves, magnetic. So I'm just saying that the signal does not always follow the, say, if you're on a network, you might say, well, I'm on Ethernet network, and then it will be in voltage waveform, like I have here, and that will represent the signal. But then suddenly we see that, hey, maybe somebody's using fiber optics in terms of connecting maybe a access switch to a core switch or to a distribution switch to get a higher throughput, and then the signal is no longer represented by a voltage waveform, but rather a light intensity, a light pulse signal. So just showing you that the signal is represented via different formats. Okay, and then we have the media itself. This is the channel which connects to nodes. Now, as I've said, we can vary the amplitude, we can vary the frequency, we can vary the phase, we can vary the rate, the clock. That has to do with the clock, the bit time. Now, this is an important definition, which is called bit time. Now, the definition for bit time is the time it takes for one bit or one binary digit to be transmitted from a network interface card operating at some predefined standard speed. The time is measured between the time the logical link control layer 2 sub layer receives the instruction from the operating system until the bit actually leaves the network interface card. So the bit time is the time it takes for a network interface card at OSI layer 2 to generate one bit of data and send it out to the media as a signal. The definition here is a little bit confusing. So as you can see, there is the bit time, and that is the time allowed for a single bit of data to be sent out on the media as a signal. And here you can see an example of the bit time. Now, the previous example may have been a little bit tricky by showing the bit time. There it says it's showing here almost 2, but I just want to show you here a single bit. There we go, the time with the single bit. All right, now there are various signaling methods, non-zero return, Manchester coding, although that will be fall more into the digital systems, and I'm not going to go into that right now. One of the major features of the physical layer is the encoding of the signal, and this is seen as the grouping of bits. Now, here is a little picture showing some of the features. Now, we have a specific physical signal pattern which denotes the start of the frame. Now, remember, the start and end of a frame is very important because the different frames need to be differentiated. Some frames might be going to different nodes on a network. So we can't just send all the signals on the transmission channel to one place. So there has to be some encoding allowing us to see when the start and end of a frame takes place. And also we need to differentiate the intelligence signal from the noise. So here we see the beginning of a frame, which is represented maybe by a certain bit pattern. There we go. Then we've got the physical signal representing the frame contents. So that's the additional layer 3, 4, and so forth headers. And then the data, the user data. And then we have the specific signal pattern which denotes the end of the frame, telling the receiver and the transmitter where the frame ends. And that is often also represented by a specific bit pattern. And then we might have all this other signal, which is not good signal, is noise data. So it is not intelligible data. While it may still seem like it's useful because it's got the same shapes and that, well, because the frame had ended, we know that what is after that is useless. It might just be modulated noise or a signal which is interference from other channels or other nodes. So then we come to the next frame, and we can see this is the start of the signal, the start of the frame, and there's the representation of the data, the framed information, and there is the end pattern. So you can see that, don't forget that within the entire bit stream, there might be parts of the signal which are useless, and that often is represented as noise, or it's comprised mostly of noise. Now, when we talk about bandwidth, we also talk about throughput and goodput. Now, many people do not know the units of bandwidth and what the measure is. For example, when we talk about bits per second, the abbreviation is BPS. Now, keep in mind, this is not bytes, it's bits. The single unit. Now let's just see if I've got a little picture here. Here we go. There's a bit, a 1. There's a bit, a 0. There's a bit, a 1. So this is bits per second, and the reason why our measure is in bits per second is because it's on the physical layer. However, when we usually talk on the higher layers, we normally talk about bytes, and that is a cluster of 8 bits. So we can see that when we measure bandwidth, we talk in terms of binary bits. So BPS, and now if we have 1,000 bits per second, we call it a kilobit per second, kbps, and then we have megabits per second, mbps. Now don't confuse that with megabytes in terms of storage. You know, when you look at your information here, I've got a little window here, and you can see I've got the size. There you can see these are kilobytes, not kilobits. And if I go further down, we might find that some of these might be megabytes or even gigabytes. So if I go and I say this, you can see there gigabytes, not bits. So here we come to bits because that's usually to do with transmission and reception of information. Gigabits per second, and then terabits per second. And nowadays we are much higher. We also have petabits per second, and in the future we'll be talking in terms of exa, zeta, and yotta. So these are very, very high bit rates. Now, just by the way, it might be interesting to see the evolution of these bit rates. Now, in the old days, I don't know if you recall, we had those modems. We used to dial up to the internet, 56K, and that was the bit rate, 56 kilobits per second. That's why it was called a 56K modem. And then we went to the ISDN and so forth. Now, just having a look at the evolution of the ADSL, which is still the most popular WAN technology. You can see we're up to VDSL, about 100 megabits per second, which is still a very fast protocol, but there are challenges in terms of the distance from the user to the interchange, whereas the fiber networks, here we got the BPON and the GPON should be somewhere here, XGPON, there we go. This solves a lot of those problems, and look, we are at 10 gigabits per second and moving upwards. And by the way, I don't know if you're interested, you can also have a look at the standard fiber cables and some of the manufacturers and how their effective speed has improved over the years. Now, just look at the Alcatel-Lucent. We were talking about 15.5 terabits per second, and that's the channel speed, and that's the distance. So you can see this is very good for underwater sea cabling. Look at that, 7,000 kilometers. And then just look at this one, NEC. We're looking at 101 terabits per second, and you can have a look at the per channel speed is exceptionally high. And I have seen one here that was petabits, which I think they are, you can see here, 1.05 petabits. So a lot in store for the future. But what I'm trying to bring to attention is we are talking about bit rates. How many bits can be sent across a channel? There you go, whether it's wireless or there we go, wireless again. So we're talking about that would be your cellular, and we are measuring the bit, the single unit, meaning how fast the actual 1 or 0 or the modulated 1 or 0 can cross the network. All right, so here we go. We look at the definition of what bandwidth means. Digital bandwidth measures the amount of information that can flow from one place to another in a given amount of time. Now, something that's very important here is it says the amount of information, but that does not mean it's useful information, because remember, there is so much control and signaling information that is attached or put on as headers and trailers onto our data. So you can see there's your data, but look, then we've got the application header and the additional OSI layer headers, and right down to the data link header and trailer. And you can see that even in the physical layer, as I said, we still have some additional signaling and control headers and trailers. So the throughput would be all the signal getting through the system or through the channel in a given time. And in this case, we say per second. That is why it is kilobits per second or gigabits per second. But now, what is the throughput? Well, what is the goodput? The goodput is a measure of the transfer of usable data after protocol overhead traffic has been removed. So that's just the data. The good put is what the user needs. So good put is a measure of usable data transferred over a given period of time and is therefore the measure of what is most interest to the network users. Throughput is the measure of the transfer of bits across the media over a given period of time. So let's look at this in summary. Bandwidth is the measure of the amount of information that can flow from one place to another in a given amount of time. It is almost like the channel capacity. Then the throughput is the measure of the transfer of bits across the media over a given period of time. And good put is the measure of useful information that the network users want. That represents the user data. Now, here is a table just summarizing some of the different physical media bandwidths. And you can see here, this is 10 bases, the old-fashioned Cat3, Cat4 cabling UTP. And you can see that it was quite slow. And then we had 100 base, which means 100 megabits per second. And again, quite slow. And then the one that we use the most now is the Cat5e, which is a gigabit per second. And as you can see, the evolution, and as we go to fiber, how the distance is what is important. Because while this 9 micrometer single mode fiber might also be giving gigabit, but look at the length of the maximum network segment, the length of the fiber cable, approximately 70 kilometers, while look at the Ethernet, 100 meters. So you can see there's a major difference between the two different cable formats. And then obviously the wireless, we've got Bluetooth. Although this Bluetooth standard is very old, we are now at 4.2, which is much higher speed. All right, and then look at, Bluetooth standard of 4.2, which is at a much higher bit rate. And then we can see the wireless media again. Also, there are improved standards at this time. Now here is just an example of some of the copper media. You all know the unshielded and the shielded twisted pair. The shielded just means it has an aluminium wrapper, and there often is an aluminium wire that runs with this, and it goes to the RJ45, and it must be touching the shielded RJ45. Those are mostly used in hospitals and installations like that, where there are various medical standards requiring for shielded cable. And then we've got the coaxial cable. It's not as popular as it used to be. We used to use this for TV antennas and also for camera analog video transmission. And here we see the simply plugging it into the network switch. Now, having a look at the copper media and the installation of copper media, we see that copper media, because it can absorb magnetic signals, it is susceptible to interference. So the place where you run the cables is very important. So you can see here I've got an electric motor, which is a drill. Maybe there are industrial machines. What happens is the magnetic field can couple into the cable and interfere with the intelligence or the signal that is traveling in the cable. So that is one of the reasons why we run the data wires separate from the power wires. And also certain electrical devices give off noise. Electrical noise, you can see here this is fluorescent lighting, and it tends to provide a flicker at the power frequency. So if your country is using 50 hertz, well, then it will flicker at 50 hertz. If you're using 60 hertz, it'll flicker at 60 hertz, and that also causes noise on these cables and through our devices. So what happens is we need to think about where we do our cable runs, and some of the rules that you could think about are: don't run the cables in parallel lines with power cables. For example, you would not put all this Ethernet cabling near power cables that are running in the same conduits or the same trunking paths. But Cat5e is quite resilient in terms of interference. Cat5e and better has got quite a good noise reduction by the twisting of the pairs, and I think there is a diagram here. Yes, so because these cables are twisted, it does reduce some of the noise that could come from nearby cables. And what people don't realize about the UTP is that the cable is twisted and then again twisted. So if I show you a little picture here, inside this connector, inside this cable, you'll see these are twisted, but this entire group of cables, these 4 pairs, are also twisted inside the cabling. So if you take a piece of the UTP, you'll see that it seems to have some sort of bumps along the way, and that is because the cable is twisted inside there as well. So that would mean that this pair, that pair, and that pair are also twisted together. Now, one of the reasons why the cable is twisted is because of something called crosstalk. Now, we twist these pairs to reduce something called crosstalk, and here is the definition of crosstalk, which is the effect by which a signal transmitted on one circuit or channel of a wire creates an undesired effect in another circuit or channel. So crosstalk is a magnetic interference from wires within the same cable. So I would like to show you a diagram of an electromagnetic coupling. Can you see I have 2 conductors next to each other? And because they are current carrying conductors, which means electrons are traveling inside there, they create magnetic fields. And because they create magnetic fields, they induce currents in the other conductor. So what happens is on network cables, you might find this happening. There we go. We have current carrying conductor over there, and what happens is it's influencing the conductor that is wound right next to it. And you can see there was a voltage signal, maybe 5 volts, which means there's a current flowing in here, and it induced a similar signal, albeit a bit smaller. Because remember, there is an air gap in this insulation. So it's not exactly the same as what is traveling in the original conductor. So it influences the cables nearby. And when we twist the pairs, what happens by twisting it, we kind of counteract that. So here we go back to the, let's see, here we go back to this conductor. And if these were twisted, if we could twist these around, well, the magnetic field that occurs here would then be cancelled out because I have twisted the cable in 180 degrees. So this is one of the reasons for the twisting of the cable. And then this is very important because when we have these magnetic fields around our cables, it induces noise in the nearby cables. So by twisting it, it protects the signal from interference. Now, while we're on this topic, I'd just like to show you something else that also is there to make the cable more resilient against electrical interference. And here we have something called shielded cables. Now, you can see this is called STP and this is UTP. UTP means unshielded twisted pair, while STP means shielded twisted pair. This is not as common. You can see each pair is shielded, but that is not as common as say, let's look at a different diagram, this one. This is more common, and that's what you will see when you buy STP cable. You can see that they're all just shielded, a shield around them, and there is the like a aluminium or wire, like a piece of wire that is conductive running along the entire length of this cable. And the point of this wire is that it is supposed to go in or be attached to the shielded RJ45. Can you see that that is not what the common RJ45 looks like? This is the shielded one. And the reason for this is to get the potential on the one side of the cable and the other side of the cable or the fly lead to be at the same level, because you're supposed to earth this side and earth the other side so that you have no potential difference or voltage difference between the one side of the fly lead to the other side. So if I show you just the fly lead here, by shielding it and connecting both sides to an earth source, you're effectively keeping this entire cable at 1 voltage potential. And the reason why people do that is because of this standard, the IEC 60601, which is a standard for connecting and of medical equipment, and that is for a very high safety in terms of getting electric shock. So if, for example, this cable had to have gone hot, or some supply cable had cut in here, or somebody had shorted this out to supply cable, to stop the patient lying in the hospital bed from getting a shock, or the patient monitor, the monitoring device, from having a fault, it will then be brought to ground because of the shield that was sitting over here. All right, getting back to the notes. Now, there are 2 standards here. There is the T568A and the T568B. For the most part, we only use the 568B standard now, and that is the orange, white, orange, green, white, blue, blue, white, green, brown, white, brown color pair. So that means that when you are making your cables, you start with pin 1 as orange white. Now, many people are not sure which is pin 1. Now, I do have a video of this, and just to put your mind at ease, so you can get an idea immediately of which is the pin 1, what happens is, if you're looking at the RJ45 itself, pin 1 is the leftmost pin with the connector facing downwards. So you can see there is the lip, and here is the bottom of the connector. So pin 1 is on the left hand side. So it's very important to get that correct. So it is orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. Now, you are welcome to watch my HD video on how to make these cables and how to make them accurately. All right, so moving on, we do have a crossover cable, which means if you would like to connect 2 hosts together, for example, if you would like to connect a let's say here a 2 computers together, if you would like to connect 2 like hosts together, when I say like, I mean computer to computer or laptop to laptop, we use something called a crossover cable. And the reason why we do that is it's only 2 hosts. So that means transmitter to receiver, and on this side, his transmitter to her receiver. So what happens is, if we look at that diagram, we'll see that it looks like this. The cable has to be transmitter, has to go to the other person's receive. And this cable here, see when it says receive, has to go to the other person's transmit. So we'll see transmit going to receive, and receive going to transmit. Can you see that it should have been transmit pin 1 going to transmit pin 1, but it's not the case. So you can see that transmit is wired to a different pin, and receive is wired to a different pin. And this is called the crossover, because we are literally crossing over the transmit and receive pinouts on the cable. So this is why we have something called a crossover cable, connecting 2 network hosts, usually 2 of the same host. Nowadays, most switches and routers can deal with that, and you don't need to have a crossover cable. The switch can knows to cross over the transmit and receive pins. It does it using software, while in older times we had to physically make crossover cables. That would mean that pin 1 would be wired to you can see pin 1 would be wired to pin 3, and pin 2 would be wired to pin 6, and so forth. So when we make something called a straight through cable, that is literally just a fly lead. That is pin 1 to pin 1, pin 2 to pin 2, pin 3 to pin 3. That is a straight through cable. So if you look at both sides of the RJ45 on both ends of the fly lead, they look exactly the same. And the best practice is to use T568B, because that is the fastest through a bandwidth cable, because we can get gigabit by doing this standard. Now, if we are making a crossover cable, unfortunately, we do have to swap the pairs, and then we will have on the one side of your cable, it will be T568A, and on the other side, it will be T56B. And then we have something called a rollover cable, and I wonder if I have a picture here. I don't have a picture here. A rollover cable is just the cable that we use. That is a serial cable with a Ethernet an Ethernet connector on the other end, mostly used for configuring routers and switches. There we go. That's the rollover cable. So you can see there's a serial interface to the Ethernet. Now, most people do not use serial anymore, so you'll find that these are you often use USB, or you just use direct Ethernet to Ethernet. Right, moving on. Now, we also had in the older days coaxial cable designs, although some people still use this, and all it really is the copper conductor with a shield around the side and then a jacket. The braid here is mostly for noise and interference, and also to provide a signal reference, and the signal will be in this little copper connector. And most times you'll find that this copper connector is no longer copper. They are using aluminium or other alloys, so we always got to be careful. And when you are doing your Ethernet cables, just make sure they are copper, because copper is going to give you the best signal to noise ratio. All right, these are just the connectors, different types of coaxial connectors. Fiber optic cables are very popular because they are immune to electromagnetic interference. Do you remember earlier I said about how the crosstalk and how the running of cables is very important? Because if we run cables next to each other, for example, if you run UTP next to power cables, we get noise coupled into the signal cables. Why? Because it's copper, and copper conducts electron flow, and therefore we will get interference. But when we talk about fiber optic, it is based on light signals. Now, if we put fiber optic cables near power sources, like maybe your supply cable or your lights, maybe your lights in your house or next to a machine, the fiber optic does not get any interference from the nearby magnetic fields. So fiber optic cable has a great advantage in that it is immune to electromagnetic interference. Another advantage of fiber optic is that it is not a theft problem, meaning in many countries, people try and steal copper cables because they will then take the cable and get it melted down and get their money for the cable. Whereas fiber optic cable, once it's in the ground, it's not of high value to people in terms of going and melting down the glass, for example. So it is not a theft. It does not have that problem of theft. Now, when we install fiber optic cable, we have to decide in terms of where we are installing it. For example, if you look at this picture here, this is the fiber to the home or fiber to the curb or fiber to the distribution box. You can see we run it usually under the in the curb, and then to the buildings or whatever, if it's fiber to the building or fiber to the curb. And you can see here that the cable is in let's put it an outdoor area, so it must have some sort of protection around it. So if we go back to this slide here, we can see that the fiber core itself is very small, but then it has to have a cladding so that the light rays do not leave the cable or the core, the glass core. Although you do sometimes get plastic fiber cables for short distances, like you might find these are plastic. You will find this maybe in cars or in high-end home theater systems, for very good noise immune audio transmissions, or especially in the car environment, because there's a lot of electromagnetic noise. We might use fiber optics, or in industrial applications and factories. So there we might use on very short runs, 2 or 3 or 4 or 5, 10 meters plastic cores. But in most cases we use glass. So the glass is there and there's a cladding, and we do need a protective covering. And here you can see it says strengthening material. Often it is yarn, or there is sometimes steel there. And I'm going to show you some photos of some steel cores that go with the fiber optic cable to give it very strong characteristic. And that's particularly important for underwater sea cabling. But anyway, in terms of the domestic use of fiber optic cable, we do not need extremely strong cables. All we really have is a nylon covering, and you might even find a nylon thread running here with the cable, just so that if you're pulling the cable too hard, the nylon thread will hold it. Right, so if you have a look, you'll see there's the core, then the cladding, then the buffer, some sort of armor yarn, and then the jacket. Now, going back to the pictures that I showed you here, you see this is a fairly strong fiber cable, but nothing compared to the ones that we would see going under the sea. Here I've got an example of underwater sea cables, which have become very popular. And I'm thinking, if you have a look here, you can see some of the cable runs, and you can see how extensive the underwater sea cabling network has become, with the glass fiber carrying so much of the world's communication. And this is just a more like a drawing of what it looks like. There are the fiber cores. There's the cladding. Okay, well, the cladding is on each one of these fiber cores. Then we've got some protective covering, some waterproofing, and these are these iron, like these iron cores that are coming with here. They've got nothing to do with signal conduction. Remember that the fiber, the glass, is the signal conducting medium, and it's with using laser diodes and light rays. But here, this this protective iron cores here, this is because of the hostile environment that some of these cables are subjected to. Here you can see a shark trying to bite through one of these underwater sea cables. And what happens is we run these underwater sea cables, and they're very long. I mean, you can imagine a lot of these are over 1,000 kilometers. So we need some sort of amplification or repeater options, just because the signal does get quite attenuated, and we do need to amplify it a bit. Now, there is a real life example of some of the cores. There is the glass cores with the cladding, and there you can see the copper waterproofing area, and there is the sheath, the almost the iron core sheath. And because it is wired like this, it does have some flexibility, but remember that we should never bend fiber optic cables with harsh bends, because the light rays will then be interfered with. So we do gradual bending with fiber optic cables. So if you go and have a look here, if you're going to run this in your street and you need to make a turn, it'll have to be a wide turn. You can't go and do a 90-degree corner with fiber optic cables. And even when it's terminated into your house, you'll see that there are loops that the installers do, because we don't want to have the light dispersed out of the the glass core. All right, so just look at this installation. You can see here is the supply, the electrical meter, and how the fiber it's not a problem when you run fiber near the electrical parts of a house. And now you see, look at that. There is giving you a closer look. There are the glass cores. So you can see how small they are compared to everything else. Now, this is an underwater sea cable. You would not buy such a cable just to put under the curb, under a pavement. This is definitely a very high tensile strength cable, which is going under the sea. And here's another diagram just showing you the cable runs under the sea, and there you can see a cable underwater there. Here's another example of it going into the sea. More cable runs. I think that's it. Yeah. So what happens is we have to look at the different applications. If it's in domestic use, well, they're not going to look like the ones I've just shown you. If they're domestic, they will look more like these ones. Now, the fiber optic media allows you to have a dedicated transmit and a dedicated receive, which means it is full duplex communication. Now, we can differentiate fiber media in terms of single mode and multi-mode. If you look at the single mode, we have one active light ray going in there. So what happens is it's a smaller core, there's less dispersion, and the benefit of this is the distance. So it uses lasers as the light source, often within a campus for backbones. So this is very high data carrying capacity. And if you look at multi-mode, well, these are normally shorter runs, but keep in mind that fiber optic cabling is far longer than any copper alternative. So when I say shorter, I don't mean 100 meters. I'm talking still way longer than Ethernet and other serial communication or WAN cabling methods. So although it says here shorter, it is shorter in terms of the single mode, but still much longer in terms of, say, copper. All right, and then this one uses LEDs as a light source, just telling you that if you are going to use lasers, remember that these are high power lasers, and that is able to activate, we call it like almost to pump in very high power. We use very high power lasers to pump in the light array into the core, and that's why it is for long distances. While the multi-mode, if you're just using LEDs, it is shorter because LEDs are not as powerful. They cannot excite as many photons into the core. Now, just closing off here, having a look at the wireless media, this means it is sent, the signal is sent over the air. The air is the medium, and obviously there are a lot of interference and aspects in terms of sending information over the air, and I think I did discuss that at the beginning of the video with the cellular aspects and in terms of shadowing and trees and weather, and we know about these things already. So I'm just going to step through here and just show you there are many wireless standards. We've got Bluetooth, Wi-Fi, NFC, all these type of standards that allow us to connect over the air, and you can have a look at that, the different IEEE 802 and the different Wi-Fi standards B, C, D, N, up to N, and so forth, in terms of the different frequency ranges of these standards. Here we go, as I was saying, the A, B, G, okay, and so forth. These are the different frequency ranges that the wireless transmissions take part in. And this is some of the devices, although these are quite old-fashioned. They don't look like this anymore. They're almost about a quarter of the size, as I showed you earlier, the 3G dongles and things like that. And they're often mostly on-board motherboards nowadays. So that brings us to the end of the lecture on the physical layer. Thanks for watching, and I hope it was informative. Cheers.